Last lecture we asked whether a die works now. Today we asked whether it works in 10 years. The data situation is completely inverted. Last time we had billions of measurements and a positive class 1 in 10,000. Today we have a few dozen parts, a few weeks of stress, and very often zero failures. From that, we have to certify a 10-year lifetime. That is an extrapolation problem, and extrapolation is a regime where the shape of your model dominates the answer. When you interpolate, most reasonable models agree. When you extrapolate 4 orders of magnitude in time, two models that fit the data equally well can differ by 100 times in what they predict. That is exactly the situation where Bayesian methods and physics-informed model earn its keep. They do not manufacture data that does not exist. What they do is make the assumption explicit and carry the uncertainty going through the answer. So the number you report comes with an honest interval attached to it. No prior background in reliability physics is assumed. I will build the standard machinery first and then show where the learning enters. A short recap and then the pivot. Last lecture the dataset was enormous and the interesting class was almost absent. The difficulty was imbalance. The answer was to score every die against its peer and then choose the operating point with an explicit cost function. Today the dataset is tiny. A qualification experiment may have 30 units per stress conditions, run for 1,000 hours and produce zero failures. The difficulty is scarcity. The sentence in the navy box is the organizing idea of the lecture. Qualification is an extrapolation problem with almost no data. The last line is the reason it is hard. If you are interpolating inside your data, almost any reasonable model gives almost the same answer and the wrong model is forgiven. If you are extrapolating 4 orders of magnitude in time, which is what going from 1,000 hours to 10 years requires, then the shape of your model determines the answer. The data merely constrains it a little. I'll show you two models that fit the same data equally well and differ by a factor of 15 in what they predict. The first segment is the standard machinery, about 15 minutes. I want you to leave this segment able to read the qualification report and know what each number means and what it does not mean. In particular, I want you to understand why a report that says zero failure in 75 units is a much weaker statement than it sounds. We will cover the standards landscape briefly and then the statistics of a real qualification, then the acceleration models, and then lifetime distribution and how extrapolation actually works. Let us be concrete about what a qualification is. It's a fixed program of stress tests that a product has to pass before it can be sold. The program is agreed between the supplier and the customer, and usually by pointing at the published standard rather than by negotiating each test. It certifies the product and the process together. That coupling matters. If you move that part to a different fab, change the package, or shrink the process, the qualification no longer applies and you requalify. And here is a point I want to press on. The qualification is a gate. Its output is a pass or a fail against a stated criterion. It does not produce an estimate of lifetime with error bars. On the right is a representative program. The high temperature operating life, 1,000 hours at 125 degrees with the part biased. The temperature and humidity bias, 1,000 hours at 85 degree and 85% relative humidity. Temperature cycling between minus 55 and 150 degrees, plus electrostatic discharge, latch up, and the rest. Each of these has a pass criterion and a sample size. Together they take months and cost a great deal of money. That cost is why the idea of doing parts of this in simulation is attractive. 4 documents. I'll name them and move on. JES-D47 is the JEDEC standard for stress test driven qualification of integrated circuits. It defines which tests you run at what conditions and with how many units for commercial parts. JEP-122 is the interesting one for this course. It is titled Failure Mechanisms and Model for Semiconductor Devices, and it is where the acceleration models live. If you want the activation energy for a particular mechanism or the form of the voltage dependence for the gate oxide breakdown, it is the document that has it. AEC 8100 is the automotive standard published by the Automotive Electronics Council. It defines temperature grades and it is substantially harder than the commercial standard. Grade 0 parts have to survive an ambient of 150 degrees. The JESD 22 series holds the individual test method definition and the order and the other documents referred to. If you read one of these, read JEP 122. It is the physics document and every acceleration model in this rest of this lecture appears in it. Now the arithmetic that everyone should see once. The common qualification criteria is 3 lots, 75 units per lot, 0 failures allowed. The number 77 looks arbitrary. It is not. Suppose a true probability that a unit fails, the test is P. If you test n units and none fail, the probability of that outcome is 1 minus P raised to n. Set that equal to 1 minus your confidence level and solve for P. That gives the curve on the left. For 6% confidence, 77 units, and the bound comes up at about 1.2%. 77 is the smallest sample that demonstrates a defect rare under roughly 1% at 6% confidence. Now look at what the statement actually is. It is the upper bound on a failure probability at a stated confidence level. It contains no estimate of the lifetime distribution. It has no shape parameter. It gives you no notion of the margin. You do not learn whether the part would have failed at 1001 hour or at a million hours. And notice the scaling. The bound goes as 1 over n. To demonstrate 100 dppm directly by this method, you would need tens of thousands of units, which nobody does. The gap between what you can demonstrate and what you need to claim is filled by models. The bathtub curve organizes the whole field, so it is worth 10 minutes of your attention over the semester, even though I'll spend 3 on it now. Plot failure rate against time in service. 3 regimes appear, and they have 3 different physical causes. The first is infant mortality. The rate is high at the start and falls. It is caused by manufacturing defects. The rate falls because the defective parts fail early and remove themselves from the population. Everything in the last lecture and burn-in attacks this region. The second is useful life. The rate is roughly constant. It causes events rather than wear. Cosmic ray induced soft errors, voltage transient, handling damage. A constant rate means the failures are memoryless, which is what an exponential distribution describes. The third is wear out. The rate rises with time. The cause is physical degradation of materials. Bond breaking at the interface, damage accumulating in oxide, metal atoms transported by current. Qualification targets the third regime. The question asks if whether the rising part of the curve stays out beyond the product's intended life. And the difficulty is that you have to answer that question from the data taken far to the left where the rise happens. Everything in reliability engineering rests on acceleration, so let us be clear about what it assumes. The problem is straightforward. You need a statement about 10 years and you have a few weeks on laboratory time. The move is to run the parts at a stress higher than it will ever see in use. Higher temperature, higher voltage, higher humidity, larger temperature swings. Degradation that would take years at use condition happens in hours. The acceleration factor is the ratio of life at use condition to life at stress condition. If the factor is 200, then 1,000 hours on a bench stands for 200,000 hours in the field, which is about 23 years. Now read the navy box, because this is the assumption everything rests on. At the elevated stress is assumed to change the rate of failure mechanism without changing the mechanism itself. If a new mechanism switches on at an elevated stress, the extrapolation is invalid. The uncomfortable part is that the data will always look perfectly reasonable anyway. You will get a clean straight line on a log plot, and it will be the line describing the wrong physics. The table lists the standard models by stress variable. The three next slides take the important ones. Arrhenius is the temperature model and it is by far the most used. The acceleration factor is the exponential of the activation energy over the Boltzmann constant times the difference of the reciprocal temperature. Temperature is in Kelvin. The physical picture is a thermally activated barrier. The degradation event requires crossing an energy barrier of height E sub A. The rate at which that happens goes as an exponential minus the height over kT. Raise the temperature and the rate goes up exponentially. The activation energy is a property of the failure mechanism. It is measured by running the same test at several temperatures and fitting the slope. Typical values run from about 0.3 electron volts for some interface effects to about 0.7 for many oxide and diffusion processes, to above 1 electron volt for some metallurgical reactions. Now look at the sensitivity, because it is that part that matters. Between 55 degrees and 150 degrees, the activation energy of 0.7 gives an acceleration factor about 190. 0.5 gives about 35. A disagreement of 0.2 of an electron volt moves the answer by more than a factor of 5. So whoever picks the activation energy picks the answer. That number deserves an uncertainty attached to it, and in practice it almost never gets 1. Remember that when we get to the Bayesian segment. 2 more models, then the common structure. Black's equation covers electromigration. Electromigration is the transport of metal atoms along a conductor driven by the momentum transfer from the electron flowing through it. Over time, a void opens and the line goes open circuit. That means the time to failure goes as current density to the minus n times the Arrhenius factor. The exponent n is usually near 2. Notice the two stresses appear together and then they are coupled. Raising the current also hits the line by joule heating, so you cannot vary one without the other unless you are careful. Iron is the general multi-stress form. It has a temperature term, an Arrhenius term, a second stress term with a cross coupling. The cross term lets the effect of the second stress depend on temperature. Arrhenius, Black and Peck's humidity models are the special cases. Now the box at the bottom, which is the point of this slide for our purposes. Each of these models is a small parametric form with 2 to 4 constants derived from a physical picture of a single mechanism. Those constants are fitted from very few data points and they enter the answer through an exponential. And the extrapolation runs far outside the fitted range. In that situation, parameter uncertainty is amplified rather than averaged away. That is the case for treating the parameters as distributions rather than as numbers. Now the distribution you fit and the data problem that comes with it. The Weibull distribution is the workhorse. Its cumulative form is 1 minus the exponential of minus time over eta all raised to beta. Eta is the scale, the time by which about 63% of units have failed. Beta is the slope and beta carries the physics. Beta below 1 means failure rate is falling, which is infant mortality. Beta equals to 1 means a constant rate. Beta over 1 means rate is rising, which is wear out. Plotted on Weibull axis as here. A Weibull distribution is a straight line and beta is its slope. Now censoring. A unit that has not failed when you stop the test is right censored. You know it survived past a certain time and you know nothing else about it. In a typical qualification, most units are censored and sometimes all of them are. Look at the plot. 5 units failed, 7 are still running when the test stopped. The field navy points plot those 5 failures against the full population of 12. The open red circles plot the same 5 failures as if they were the whole population, which is what happens if you simply delete the sensor units. The two fits differ. The correct maximum likelihood function has a separate term for survivor and it has to be used. This is the single most common error in reliability analysis. One more thing to note is about the shading. The band marked in the range of failure fractions the test actually observed, roughly 10 to 60%. The claim is a 0.1%, 2 decades below it. Raising the temperature gets you failure sooner, but it does not get you failures at a lower probability. That gap is where model does all the work. This slide is the argument for everything in the second segment. Weibull and log normal are both standard lifetime distributions. Both appear in standards. For most real data sets, both fit the observed range acceptably, and a good of fitness test run inside the data will not clearly prefer one. They differ in the lower tail. The Weibull has power law lower tail, so early failures fall off gently. The log normal details match faster at short times. The disagreement between them grows as you go lower and lower failure probabilities. Look at the plot between 6% and 90%, which is the shaded band where failures were actually observed. The two curves sit almost on top of each other, go down to 1 part per million, which is the level a customer cares about, and the two models disagree about by a factor of 15 in time. Read the navy box. Two models that feed the same data usually differ by 15 times in the answer that matters, and you cannot choose between them by using the data you have. That is the situation. The response is either to pick one and hide the assumption, which is common, or to carry both and report the resulting uncertainty, which is what the next segment is about. Burn-in bridges the two lectures, so it gets a slide. Burn-in attacks the left-hand region of the bathtub curve. Hold parts at elevated voltage and temperature for some hours, and parts with latent defects fail on your equipment instead of at the customer. Early life failure rate testing is the measurement version of the same thing. Stress a large sample for a short time and count failures to estimate the rate in the first months of service. Burn-in is expensive. You need ovens, burn-in boards, sockets for place and handling. And there is a real risk that stress itself damages good parts, which is overkill by another name. So the same calculation from last lecture applies. Burn-in cost per part against the escapes it removes. The table shows the policy options. Burn in everything in the historical answer. Burn in a sample per lot monitors the rate and removes nothing from the ship population. Burning in only the parts a model flags in the model is the modern answer, and it gets close to the full coverage if the model is good. The last row is where the two lectures meet. The risk model is built from the test data, which was lecture 1. The decision it drives is a reliability decision, which is lecture 2. Second segment, about 22 minutes, and this is where the course content connects. 4 topics. Bayesian inference with sensor small samples, which replaces a point estimate with a distribution. Active learning, which chooses stress condition instead of accepting a fixed matrix. Physics informed surrogates for the degradation mechanism themselves, and finite element surrogates for packaged thermochemical simulations, which is the virtual qualification data. The last one connects directly back to the thermal co-design homework, and I will point at that when we get there. Framing for all 4 is the same. None of these methods create data. What they do is structure prior knowledge efficiently and then report honestly how much is still unknown. Bayesian inference is the natural fit for this problem, and it is not exotic. Start with the likelihood, which you already made. A unit that failed at time t contributes the density at time t. A unit that was still running at time t contributes the survival function at time t, meaning the probability of lasting at least that long. Multiply them. Censoring is handled by construction. Next, the prior. This is the piece that matters here. You are not starting from ignorance. There are decades of published activation energies and Weibull shape parameters for known mechanisms. If the literature says the shape parameter for this mechanism is around 2, a prior centered on 2 with a sensible spread is honest, and it stabilizes a fit that 10 data points cannot stabilize on their own. The deliverable is the posterior. It is a distribution rather than a number. Look at the plot. The red line is the maximum likelihood point estimate, 13.4 years. Against a 10-year requirement that reads as a pass, and in a report it would be one number in the table. The Navy distribution is the posterior. Its 90% credible interval runs from 4.2 years to 27 years. 4.2 is below the requirement. The honest statement is that the requirement is probability met with a real chance that it is not, and here is the probability. Those are different engineering conclusions from the same data. Let me make the prior concrete because people often are uneasy about it. The Weibull shape parameter. With 5 failures, you cannot estimate the shape parameter reliably. A prior build from published values for the same mechanism and from previous generations of the same product prevents you from reporting a shape of 0.4 where the physics says it should be near 2. The activation energy. Today it is taken from JEP 122 and used as a fixed number. Making it a prior with a spread does not add an assumption. It makes the assumption visible and lets the uncertainty flow through the answer. The voltage exponent for breakdown models. Same story. Lot to lot variation. Qualification uses 3 lots for a reason. Lots differ. A hierarchical model represents that explicitly with a lot level distribution and a unit level distribution instead of pulling everything. Now read the Navy box because it is the argument. When a qualification report assumes an activation energy of 0.7, that is already a prior with 0 variance. It is the strongest possible prior and it appears nowhere in the report as an assumption. Replacing it with a distribution is a weaker assumption stated openly. Hierarchical models are the natural extension, sharing information across lot, across stress condition, across product generations. The second place learning enters is in choosing the experiment. A standard qualification uses a fixed stress matrix. 3 voltages by 3 temperatures spaced evenly decided before any data is taken. The left panel shows that. It is a simple plan and it spans units evenly, including at conditions that turns out to tell you nothing. Active learning replaces that. The right panel shows the idea. The shading is how informative each condition is about the quantity you care about, which is the lifetime at use condition. The path shows condition chosen in sequence. A loop is on the right. Feed the posterior over model parameters using everything measured so far. Score each candidate stress condition by the expected reduction in uncertainty about the use condition life. Run the best one. Repeat until the credible interval is narrow enough or you run out of units. This is Bayesian optimal experiment design and it is a mature field. The objective is information about the answer and not coverage of the stress space. One constraint that has to be enforced by physics rather than by the algorithm. The optimizer will happily push toward a high stress field because that is where failures happen. Very high stress is also where new mechanisms activate and the extrapolation becomes invalid. Bounding the design space is the engineer's job. The third place learning enters is inside the degradation model itself. The important mechanisms have known functional forms. Bias temperature instability, shown in the plot, follows a power law in time with an exponent around 1/6, an Arrhenius temperature term, and a strong power law dependence on voltage. Time-dependent dielectric breakdown has its own form. Hot carrier injection has another. Now consider what happens if you throw a flexible model at this data. You have a handful of experiments over a decade in time and you need to extrapolate 8 decades. A neural network with no constraints will fit those points exactly and do anything at all outside them. A physics-informed approach constrains the model to obey a known form. The exponent and the Arrhenius structure are imposed rather than learned. Learning is then used for what physical form leaves open, the coefficient, how degradation happens on the actual workload rather than on a constant DC stress. Recovery, because BTI partially recovers when the stress is removed. And device-to-device variation, which matters enormously at small dimensions. The result extrapolates in a controlled way because its long-term behavior is set by physics, not by the fit. The table lists 4 mechanisms you will meet most often, and each one degrades. The fourth place learning enters is package simulations. Package failures are mechanical. A package bonds silicon, solder, copper, mold, compound, substrate together. Those materials have different coefficients of thermal expansion. Every temperature cycle strains the joints between them. Eventually, solder joints crack, underfill delaminates, or the die wraps enough to break a connection. Finite element analysis predicts this well. It is a standard tool. The problem is that one run takes hours, and a design study that varies geometry, material cycling profile needs thousands of runs. The surrogate argument is on the right. Run a finite element model a few hundred times spread over the design space. Train a model to reproduce its output. Then do all of your exploration with the surrogate. Left plot shows the two things you need to check: accuracy on held out designs and the cost comparison. 6 hours for one solve, about 1800 hours to compute to build the training set, and under hundreds of a second per surrogate evaluation afterwards. Now the callback. This is exactly the machinery for your thermal co-design homework. There are expensive functions. The expensive function at the thermal solve and a Bayesian optimizer search the design space. Here, the expensive function is the thermochemical solve, and objective is cycles to failure. The method transfers unchanged, only the objective is new. Third segment, we are going to walk one exploration end to end and then break it. The reason to do this is that the failure mode I'm about to show is not exotic. It is the ordinary way that reliability claims turn out to be wrong, and it is invisible in the data you have. Here is the setup, and I want to stress that every step is ordinary. The requirement is under 1% cumulative failures at 10 years at use condition. This is a typical number. The experiment uses 30 units at elevated voltage and temperature, stressed until the acceleration factor says you have covered the equivalent of 1 year at use conditions, also typical. The observation is a handful of failures, all early in test, and they follow a clean power law when plotted. The analysis fits a Weibull to those failures, handling censoring properly, and converts to use conditions with the Arrhenius factor from the standard and extrapolates to 10 years. The result is about 1% failures at 10 years. The part passes. The report is 1 page long and it goes into a folder. Read the box on the right. Nothing in that procedure was careless. The sample follows the standard. The distribution is the usual one. The acceleration model is the standard names for this mechanism. The fit is good and the residuals look fine. The report will be accepted, and the conclusion can still be wrong by 2 orders of magnitude. The next slide shows why. Here is what is happening. There are 2 degradation mechanisms, not one. One has a much larger shape parameter, meaning its failure rate rises very steeply once it starts. A large shape parameter means the mechanism contributes essentially nothing early and then turns on sharply. Inside the measured window shown, shaded, that second mechanism is completely invisible. It contributes failures at a level of 1 in 100,000, where you can only resolve 1 in 100. Every diagnostic you have says one mechanism, and the fit quality gives no warning. Beyond the window, the second mechanism dominates. At 10 years, the single mechanism fit predicts about 1%. The truth is close to 100%. That is a factor of 100, and it is the difference between a healthy product and a recall. Residuals look fine the entire time. That is the part to internalize. Goodness of fit inside your data tells you nothing about the extrapolation outside it. Read the navy box. This error is not statistical. More units in the same window do not fit it. It is structural, meaning the model form itself was wrong, and the only different thing, the evidence resolves it. So what actually helps? 5 things, and none of them are exotic. First, test at more than one stress level and check the model holds across them. If a single mechanism governs, the fitted parameter should agree across stress levels. If they disagree, that is your signal that something else is happening. This is the single most useful check, and it costs only splitting your units differently. Second, fit mixtures rather than a single distribution. Let the model contain 2 competing mechanisms with a prior on each. When the data cannot resolve the second one, the posterior says so by staying wide. That is exactly the information you want, and a single distribution fit throws it away. Third, use physical failure analysis. Cross-section the parts that failed and find out what exactly broke. Knowing the mechanism physically is worth more than any amounts of car fitting because it tells you which model foam is right. Fourth, report an interval and state the assumptions behind it. A number with a credible interval and a named model assumption can be audited. A single number cannot. Fifth, instrument the field and keep watching, which is the closing topic. The footnote is the honest reason these are not universal. A qualification is scheduled as a gate to be passed before a product ships, and everything on this list costs time. Last 5 minutes. This is the newest topics in this module, and it is where the industry is putting significant effort right now. The idea is simple to state. Stop treating qualification as a one-time gate before shipment and start treating reliability as something you measure continuously over the life of a product. Here is the picture. Gray and navy tracks are the population. Ring oscillator frequency drifts over years as the transistor age. That drift is expected and is designed for with a guard band. The red trace is one part aging much faster than the population. Nothing has failed yet. It is still inside the guard band for the first several years, but its trajectory crosses the performance floor well before the population does. If you can see the trajectory, you can act before the failure. Schedule maintenance on that unit. Lower its clock frequency to buy margin. Retire it during planned downtimes instead of losing it in service. The loop on the right has 5 steps. Measure the monitors periodically. Compare each part against the population and against what the aging model predicts. Predict remaining useful life for that individual part. Act on the prediction and feed real field degradation back into the next qualification and the next design. That last step is the one that changes the discipline. Today, qualification is done once and on a small sample before shipment. With field telemetry, the population itself becomes the experiment running continuously at the real use conditions with million units instead of 77. Step back to the course arc. Design sets margin, guard bands, and where monitors go. Test screens the parts and decide which ones get expensive treatment. Qualification stresses a sample and produces a lifetime statement. The field generates telemetry and aging predictions, and that field data becomes an input to the next design. The box in the middle is the point. Each stage in this module produces data that an early stage can learn from. Digital twin stops being one-way forward simulation and becomes a loop that measurement corrects. 2 concrete consequences. Design margin today is set by the worst case assumption because worst case is all you have when you cannot see the field. Real field data replaces those assumptions with distributions. In practice, that usually means less margin and more performance because worst case stacking is very conservative. And qualification today is a gate that is passed once. Continuous measurement turns it into an estimate that gets better over the product's life, which is a different relationship with the number entirely. 6 things to take away. 1. Qualification is extrapolation from almost no data. A few dozen units, a few weeks of stress, often 0 failures, and a 10-year claim at the end. 2. 0 failures in 77 units is an upper bound on a probability at the stated confidence. It contains no lifetime distribution and no shape parameter and no notion of margin. 3. Acceleration models are small parametric forms whose constants enter the answer through an exponential. A 2/10 of an electron volt disagreement about the activation energy moves the answer by more than a factor of 5. 4. The model choice dominates the extrapolation. The data you have cannot settle it. Weibull and log normal fit the same measurements and differ by about 15 times at 1 parts per million level. 5. Bayesian methods and physics info models do not create data. They make the assumption explicit and use prior knowledge efficiently and report an honest interval instead of a single number. 6. Field telemetry turns one-time gate into a continuous measurement. The population in service becomes the experiment at real condition and at real scale. Those 2 lectures together complete the arc: process, structure, yield, test, lifetime. One closing thought that spans both lectures. In both lectures, mathematics was standard. Outlier detection in the first, maximum likelihood, and Bayesian inference in the second. None of it is beyond a first graduate course. The hard part in both cases was the same thing, writing down what the answer is worth and how wrong it could be. Lecture 1 asked for a cost function. Building a screening model is easy. Justifying where to put its threshold requires putting a price on the escape and the price on the scrapped good die, and that argument is harder than the model. Lecture 2 asked for an interval, fitting a lifetime distribution and extrapolating it easy. Stating how much of the answer came from the measurement and how much came from the assumption is the real work. Both of these are habits rather than techniques, and both transfer to any problem where a model output drives a decision whose errors are asymmetric, which is most of the problems worth working on.